Okay. So let's talk about those radial distribution. P of R and really what we're talking about here, it's related to the probability of finding an electron in an atom in different orbitals. Probability. Finding an electron is determined by the distribution function which we're going to give the symbol P of R. I don't remember if that's what your book does. How many people have been reading along with the book? It's okay, you can be honest. Based upon responses, very little. That's okay, it's a garbage book. I really don't think there's a good book for quantum chemistry. That's why I use like 7 of them. There's one that's really close, and if they ever fix all the errors and the examples, that's what we'll be using. But we got a while till then. So we have this distribution function, and we multiply it by R. Whatever distance from the nucleus, dr. A 1s orbital. Let's talk about that one, and it will give us an idea. I think that's all we're really going to discuss. Dr. Hansen has developed an activity I think we're going to try next time, or when we don't have a Quizlet, on plotting these and visualizing this stuff too, so you can see it a little bit better. P of R is equal to 4z squared, oops, that should be capital Z, cubed, z cubed over a naught cubed, r squared e to the 2. So all this really is, if you're thinking about R times R squared. If we wanted to get like the probability of finding that function, we would do that, right? So that's what it's related to. So let's try to plot it. What we're going to have on our y-axis is that distribution function. And we're going to have our radius on our x-axis. What does this function look like for a 1s orbital? Any ideas? What's the electron density at a radius of 0? Should there be any electron density there? A radius of 0, where are we in the atom? The nucleus. Should there be any electron density there? No, something's gone horribly wrong. We're violating the uncertainty principle. If that does happen, some bad stuff happens. So there should be a point of 0 here. That's the only time it actually touches 0. What about as we go further away from the nucleus, what's going to happen to the probability of finding the electron? It's going to increase. It's going to go up. And then it's going to get to a maximum. And as we go further away, what's going to happen? It's going to decrease. Okay. As we get further and further away, what happens to the probability? It approaches zero. Is it actually technically ever zero? No, but it approaches zero. Okay. Now, kind of a neat idea, which we're going to show in a minute. That maximum value. Anybody have an idea of what the value of it is? It's definitely not 1. Any other ideas? And this is a really cool spot. It is the Bohr radius. So something that was empirically determined / theoretically determined from an old model. What we find is it's a naught. That's the maximum probability of finding it. So again, we have this connection to experiment, and we have a connection to an old, incomplete theory. So we've built on it, and we know we're getting closer to the true answer, or the right way to model this stuff. Okay, you want to talk about where does this distribution function actually come from? Does that sound good? Okay. Because you will be asked like how, especially I think on the next Quizlet, like calculate the distribution function for something. And that's always an ACS question. Like, what does the distribution function look like for some orbital? Yes. Maybe. Depends on how much time we got left. How are we doing on time? Oh yeah, we got plenty of time. Quizlet question now. It's a question, where does the distribution function come from? So we have that as our generic way to get a probability, right? We have some value from A to B, and that's equal to our probability. For an electron and an H atom, what does psi depend on again? Yep, we have a radial function, so R, and then an angular function that depends on theta and phi. How many integrals do I need to integrate that thing? Yeah, I'm going to be lazy. We're not going to write any of the limits. And we have R. Do you want me to write the subscripts and what this stuff depends on, or do you feel okay without them? Anybody want them for mathematical formality? No? All right, I like it. Okay, so we got R star, Y star, R, Y. What else do I need for the integration stuff to tack in there? R squared. Yep. Yep. Okay. What we're going to do next is we're going to slap some stuff together. We're going to combine all the R stuff and all of the angular parts. Right, so we have our R terms, Our other stuff, this, what's the value of this thing? Yep, this is 1. So we're left over with this. 0 to some value of r. Okay, rather than writing this thing out over and over again, how could we incorporate our radial distribution function into this? Well, we could just be lazy and say, that's P of R. That's our distribution function. So those are all tabulated in different spots. You can look up the distribution functions. If you compare that to the table I gave you last time of the radial functions, all you do is square it and then tack on r squared. And that's a distribution function. So depending on where you look, you can just find that part. It's really advantageous because then you don't have to do all the, I would say, tedious mathematics to get to that point. And you can just look up that value, integrate, and you're good to go. Okay. Any questions about that? Okay, I told you this was the maximum probability, but how could you calculate it? Or this radius has the maximum probability. How can you find that? That's what I want to talk about next. And that's the last thing we'll do. Okay. Then we are done with single electron systems. We'll be moving to multi-electron atoms next. Ooh. If you can, I gave you guys some handouts to look over. Wow, that one has a lot of yellow on it. Anyways, you don't really have to worry about those for the Quizlet, but we're going to be talking about orbitals and valence bond theory. So over the next couple of weeks, kind of read those through. One of those was written by my advisor's husband, Johann Aschbach, and he has some particular thoughts about orbitals that, depending on how you talk to orbitals with, that's the language you kind of want to use. So check that one out. It's like why Dr. Ogawa doesn't like to use the words delocalized or conjugated. There's stuff in there. We all know what we're talking about, but yeah. Anyways, back to what we were talking about here. We want to determine the most probable radius at which electron will be found, and it occupies a 1s orbital. Hydrogen atom. I already told you the answer. What's the answer going to be? Yep, it's going to be the Bohr radius. But we have to think about ways to try and show that mathematically. Does most probable translate to expectation value? No. An expectation value is what you would measure over many, many measurements. It doesn't necessarily mean it's the most probable. It's like we talked about with exam scores. If I have 100, 150 as my exam scores, somebody math it, what's the average? I should have picked easier divisible numbers. 250 divided by 3. Go math brain. 83. Oh, you're good! Woo! 3333. Okay, percent. So this would be the expectation value for the grade, right? But this is a quantized system. What's the most probable one? 100. So expectation value doesn't mean most probable. It means the average value, right? You feel like you understand the difference there. Okay, so now we got to find the maximum of this plot. What are some tricks you know from calculus to find maximum? Right. Find where the slope is 0. Okay, what's our y function? P. What's our x, or excuse me, yeah, what's our x value? Radius. How do you find where the slope is 0 of a function? Derivatives, changes. What are we going to take the derivative of and with respect to? Yep. We're going to look at that. So what that means is we just need dr of our radial function. I told you guys the radial function for this system. And what do we need this to equal? Yep, we need it equal to 0 because the slope at here, what value should it be? 0. Where's the only other spot where it will technically be a 0 on this plot? At 0 because the density is 0. Okay, so got to do some math. You do that. I'm going to pull out this term out front because this is just a constant. Differentiating, what rules are we going to have to use? Yep, we're going to need product rule.
Oh, yeah. That's the wrong word.
Oh, yeah. And what'd you say?
I said power rule.
Power rule, that is a different rule, but
It starts with P.
yeah, it's in the ballpark. We got product rule, what else with this ugly thing? Chain rule. Okay, product rule. I hate the chain rule.
It's better than the quotient rule.
Okay, quotient rule sucks. We can all agree upon that.
You always convert it so it's product rule.
Favorite? Yeah, exactly. That's what I always say. Because product rule is so much easier. Quotient rule sucks. But then when they're like, you have to do it through the quotient rule, why? Like, same thing with the sine, like trigonomic functions. No, it can all be sines and cosines. Stop it. I mean, it's a lower tier rule compared to the product rule. We can agree to that, right? Yes, sure.
Can we have a day where we break all the different rules?
If you want to give yourself PTSD, sure, I don't mind. All right, product rule. What's product rule? Yep. Yep, give me a derivative of that guy. 2r, I love it. Okay, plus the first times the derivative of the second, which is gross. What's that? Yep. Times. Yeah. I changed brackets. Why did I do that? Okay. We can reorganize. We can combine things. What's this all equal to again? Okay. What's something that you see throughout this? See Z? Z will be 1. We'll deal with that later. Because we can use this applied to any 1s orbital right now. What are we trying to solve for again? Yep, we're trying to solve for the most probable radius, r. So we got to isolate r by itself. What would you do to make this easier, given that this side is equal to 0? You can get constants out and reorganize. You could pull out r. That's not the one I would pick. I'd get rid of these big ugly things. Move them over to the side with 0. We don't have to worry about them anymore. What could we do with this thing? Yeah, multiply it to the other side. So we're going to get that also to 0, get rid of all that gross stuff. And what we should be left with, what other, we can do 2r plus, actually it should be minus 2z a naught r squared. That's all equal to 0. What would you do from that point? I think you suggested it earlier. I'd get rid of an r. So now we're at 2 minus what next? Yep, we could pull out 2 and move it over to the other side. What next? Yeah, we could do that. What next? Yep. Yep. In this case, since we're dealing with an H atom, we wanted to keep this somewhat generic. So we could apply it to any other nuclei we see, and then Z is just 1. So what's the most probable radius that we calculated? Yep, which is what again? Yeah. So radial distribution functions that you've probably seen in the past, they're actually just tied to the radial part of the wave function. And you can calculate the most probable location of any electron in any system that you want to check out for a 1 electron system. Are there any questions about that one? Understanding that concept and drawing the mathematics to it's pretty important. What we're going to do next time, we're going to start looking at multi-electron systems where, again, we're going to go through the Hamiltonian. We're going to run into a problem where we have too many electrons, too many unknowns, and not enough equations. And we're going to start having to make some approximations. And that's what orbitals are all about. They're actually approximations to a Schrodinger equation. So if you notice, we'll talk more about that next time. Okay? Any other questions?